Hello everybody. Welcome to Sensilo's webinar on PFAS in water and wastewater. Before we start with the actual content of this webinar, I would like to address a few organizational points. And to that end, I will share my screen. This webinar is being recorded. If you have not already done so, could you please mute your microphone and switch off your camera if you are not a speaker for this webinar. If you have any questions for the organizer or the presenters, please use the chat box to post your question. At the end of each presentation, there will be some time to answer questions, and we will try to address as many as we can during the webinar. If we do not manage to answer all questions straight away, we will make sure you receive an answer to your question by email. After the webinar has finished, or if you're listening to the recording of this webinar, you're welcome to submit any additional questions or feedback. And for that, please use the mail address support@sensilo.app. Today's topic concerns a growing problem for water quality, the presence of PFAS in water and wastewater. Last week, Sensilo published a podcast on the rapid detection and monitoring of PFAS in water, featuring an interview with one of the speakers today. And this podcast is available through Sensilo's Toolbox. Today, we will dive a bit deeper into this subject, and we will take a closer look at the development of an electrochemical PFAS sensor based on the principle of molecularly imprinted polymers, explore the pros and cons of various treatment methods for PFAS, and discuss the importance of rapid monitoring for the effective removal of PFAS. Our first speaker today is Dr. Najmeh Karimian of the Department of Molecular Sciences and Nanosystems at the University of Venice in Italy. She has a background in analytical chemistry and has been working on electrochemical sensors based on molecularly imprinted polymers for the last decade. Najmeh, would you please share your presentation? The floor is all yours.
Good afternoon, everybody. Thank you, Corina, for your presentation, and thanks for giving this opportunity. Thanks, Corina, for giving this opportunity for sharing this experience and work that it was developed in our department, in our laboratory for electrochemical detection of a member of a family of perfluorinated alkyl compound. So let's start with a brief discussion of properties, chemical and physical, of per and polyfluoroalkyl substances. So per and polyfluoroalkyl substances, they are largely man-made chemicals that they are composed of different number of fluorocarbon chains as a tail and a diverse functional group as a head. So substitution of all hydrogens in the structure by fluorine and each carbon, we have perfluorinated alkyl substances. So this can be divided based on the functional group in two different groups, like perfluorocarboxylic acid, including perfluorooctanic acid, and perfluorosulfonic acid, including perfluorosulfonate. PFAS and PFAS that are the most widespread compound and also the most toxic compound in this family. Due to the special and unique properties that this family they have, such as the high strength carbon fluorine bond and having both hydrophobic and olophobic nature, having surfactant properties, they can use in many different chemical products as industrial or in consumer. So let's see what is the main origins of perfluoro or PFAS compound. These compounds, they were invented in 1930s, and then because of their unique properties from 1940, they were used in many different applications like consumer and industrial because of, as before I mentioned, because of having these hydrophobic and hydrophilic properties. So also because of this, having this highly property of hydrophilic, they can strongly diffuse in aquatic environment. So the most concentration, the higher concentration of PFAS can be detected near to industrial site, in landfill site, and then these sources drained to environmental water, and then in drinking our drinking water. So more than 4,700 PFAS, since they are highly persistent, toxic, and bioaccumulative, so they have a big problem for environmental and for health. In Europe, based on a study, it's estimated 100,000 sites that can emit PFAS. And for example, based on the study that it was done in 2007, that they study on the distribution of PFAS in 14 major European rivers. For example, as you can see in this figure, the Po River in Italy is contaminated with many concentration of PFAS. The total estimated flux of PFAS from European rivers, it was down 43 tons per year. The PFAS can accumulate on human blood and have a negative effect on human health. Half-life for eliminating PFAS in human, it is 5.4, and about PFAS, it is 3.8. The cost of society arising from PFAS, also it is high. It is based on annual related cost. It is 52 to 84 billion euro per across the Europe. So monitoring PFAS component, it is very important because we need to know better about our environment and our human health. So detection of PFAS in aqueous environment is limited by the low concentration in order of nanogram per liter. Attention limits have been set for PFAS in water and differ slightly from country to country. For instance, the US EPA announced the lifetime health advisory level of the combined PFAS and PFOS in drinking water to be 70 nanogram per liter. Since these alarm limits are in the sub-nanomolar range, methods and devices that used for detection of PFAS must be extremely sensitive. The usual analytical method used for detection of trace level of PFAS, they are based on highly sensitive chromatographic methods coupled with mass spectrometry, such as HPLC mass, GC mass, LC mass. However, they are limited by high instrumental cost, technical skill, sample pretreatment, long analysis time. An average cost for doing each sample, it is around 200, that it is prohibitive into monitoring routine or don't allow to do sampling and testing for common PFAS. So a simpler, faster, less expensive on-site technique, and of course sensitive and reliable techniques needs to do for measurement. So this feature can be addressed through the development of PFAS detection sensor. But let's see how sensor can useful to detect the PFAS even in low amount of analyte. So before that, let's have a short introduction about the sensor. Sensor is a device that transfers chemical information into an analytical useful signal. A sensor consists of two main components: transducer, which transforms a response to a detectable signal, and recognition element that usually it's modified or functionalized with different material. So between different transducer, electrochemical techniques, because of easy of measurement, availability of instrument, higher sensitivity and specificity, less expensive, portable, rapid response time, and able to miniaturize, have been attracting attention. However, most electrochemical techniques, they don't have enough affinity or specificity against the analyte. An effective way to bring a specific chemical selectivity into the recognition layer can be by using molecularly imprinted polymers or MIP. MIPs can be characterized by high affinity and selectivity to the analyte, high stability in harsh condition, chemical and thermal, ease of preparation, and low cost. So let's see how we can prepare molecular imprinted polymers. Development of MIP is inspired by the lock and key fit principle. In fact, molecularly imprinted polymers are synthetic polymers that can be prepared by polymerization of suitable functional monomer in the presence of analyte as a template. So first, monomer through the functional group and via covalent or non-covalent interaction form a complex with target. After that, in order to stabilize the structure, we do polymerization. There are different methods for doing polymerization. One of the most useful, it is electropolymerization. Electropolymerization indeed is a one-step polymerization that in this case we have an electrosynthesized film attached to the surface of electrode. The thickness of the film is well controlled by the amount of charge passed, and this technique facilitates miniaturization that it is important, for example, for having sensor. After doing polymerization, in order to activate the sensor, we need to remove the template. For removing template, we should check different methods. Usually using solvent or mixed solvent can be useful for removing template. After removing template, then MIP is ready for rebinding the analyte selectively. So I can say that in this way, actually, we can construct a lock for a desired key. So for having an electrochemical MIP sensor, and in order to do electrosynthesized polymer, first we should choose a monomer that it is electroactive. Using a monomer that it is electroactive, the polymer can be conductive, like polypyrrole, can be non-conductive, like polyorthophenylene diamine, and can be non-conductive but by over-oxidation and a conductive polymer, like polypyrrole. The analyte we can use for detection can be electroactive. If the analyte it is electroactive, then using direct electrochemical measurement, we can monitor the current that with increasing the concentration, the current also it is increasing. But the problem is coming when our analyte it is non-electroactive, because in this way, we need to do indirect voltammetric measurement. For this, we need to have a redox probe. And in this case, by increasing the concentration, the current is decreasing. I can say that a further interesting feature of MIP is that using MIP, electrochemical sensor can have this possibility to detect also non-electroactive analyte. But let's see how it's performed. After preparation of MIP sensor and after removal template, as you can see here, we have cavity. This cavity, actually, when we prepare the polymer, after removal, the cavity that generates, it is complementary to the size, shape, and functional group of analyte. So when we dip the MIP sensor in the solution containing analyte and, of course, a redox probe, there is a competition between analyte and the redox probe for this imprinted site. So since the cavity, it is a memory of analyte, so in this competition, analyte can trap in the cavity. So as you see, using different electrochemical techniques, for example, in this case, differential pulse voltammetry, without putting electrode in the solution of analyte, we have a big current. As soon as we put the electrode in the solution containing analyte, the current is decreasing. So based on this principle, we develop an electrochemical sensor based on molecular imprinted polymer for detection of PFAS in our group in Ka Foscari University. So first, we prepare a solution containing orthophenylene diamine as a monomer, and PFAS, it was like an analyte. So electrodeposit of polyorthophenylene diamine was performed by cyclic voltammetry on the surface of a clean gold electrode. Then, after preparation of MIP, the electrode was subjected to a solution of mixed ethanol, methanol, and water for 20 minutes. Removal template generated three-dimensional cavity. Then the electrode is ready for all characterization. I should mention, since the cavity in this case, I mean, they are the point and the For example, when we see the high current, for example, here, it means the cavity it is ready. And then after putting in the solution containing the different concentration, the current is decreased. Okay, so we should be sure that this change of current, it is because of cavity, because of free cavity, or it is occupied cavity. So for this reason, we need to have a control electrode. So for this reason, we need to prepare another electrode that we call this non-imprinted polymer. I mean, for preparation of this electrode, we do the same procedure, just without adding analyte as a template. So we do all experiment in parallel for NIP sensor and also for NIP electrode. In order to do a characterization, we use different electrochemical technique like cyclic voltammetry and differential pulse voltammetry. So we use ferrous and carboxylic acid like a probe. So as you can see here, after doing polymerization, we didn't see any current. If you compare the bare electrode and the response after polymerization, you see we can confirm that an insulating polymer covered completely surface of electrode. Then after removal template, because of creation the cavity, we see redox peaks. And then putting the electrode in the solution containing different concentration of PFAS. As you can see, by increasing the concentration, the current it is decreasing. It is because the analyte it is trapped in the cavity and block the flow of probe to access the surface of electrode. So in order to do quantitative measurement, we use differential pulse voltammetry technique that it is more sensitive than cyclic voltammetry for analytical measurement. So after preparation of mixed electrode, the PFAS was removed using solvent extraction, and then putting in solution of ferrous and carboxylic acid, we recorded the background current measurement that we call this E0. Then we dip the electrode in the solution containing different concentration of PFAS, and we recorded the DPV after each 15 minutes that we consider this as a incubation time. So I should mention that when we prepare the electrode, of course, we need to optimize all different parameters. I mean, for preparing the electrode, we need to optimize the number of cycles for polymerization, the concentration of OPD, the concentration of template, the incubation time. All these parameters needed to do optimize. So at this time, for doing an analytical performances, we use the optimized electrode. So after removal, we put the electrode in a solution containing different concentration, and recorded DPV showed us that the current it is decreasing. It is because of increasing concentration that trapped in the cavity and block the flow of redox probe in order to arrive in the surface of electrode for doing an electrochemical reaction. So plotted data in calibration curve indicated that we had two linear range, that they had two different slopes. First part has a higher slope, and the second part lower slope. So for calculation the limit of the detection, we consider the first part of calibration plot, and with that we found the limit of detection 90 nanogram per liter. The Veneto region in Italy has established a threshold of 30 nanogram per liter that our sensor is able to detect the PFAS. So in order to verify the applicability of the sensor, using some water sample with a spike known amount of PFAS, we measure the concentration of PFAS, and then the results were compared with data obtained with HPLC mass. As you can see here in the table, and it reported, there was a good agreement between the results obtained by our sensor and the results we received from HPLC mass analysis. One important thing about the fabrication a MIP electrode, it is selectivity. So in order to investigate the selectivity of MIP sensor, after preparation of MIP and activated, we immerse the MIP sensor in a solution containing a specific amount of PFAS. In this case, it was 2 nanomolar of PFAS. Then, in absence and in the presence of some compound that can be interference during measurement, we record the current again. And as you can see here in the table, the sensor had a good affinity related to PFAS, since the changing of current in the presence of this compound in the same concentration or even 10 times more, it is not too much. For more detail, maybe you can find the paper in that it was published in AC Sensors, and all information about the preparation and the analytical performance, it was reported there. Screen printed electrodes offer advantages such as low cost, easy to use, and portable, make of different material like carbon, gold, and can be very easy to use when we are going to shift the experiment from the laboratory into the field. So development of MIP sensor and using electrochemical technique in the future can help for doing cost-effective in situ measurement. To conclude, the combination of electrochemical technique and molecularly imprinted polymer is an attractive approach for the development of PFAS sensors. So the sensor is characterized by low cost, wide linear range, low LOD, high selectivity, and statistical stability. The MIP sensor is suitable for rapid screening of PFAS in water sample to detect alarm situation, to be later confirmed in lab by HPLC mass analysis. I would like to thank our group in Department of Molecular Science and Nanosystem in Ca' University, in special Professor Paolo Ugo, who was supervisor of PFAS project, and Dr. Angela Stortini, Professor Ligia Moretto. Also, I would like to thank Promoting Innovative and Knowledge Office in Ca' that with their kindly support, the results and the electrochemical sense, our electrochemical sensor was invented as a patent. I would like to thank Sensilo teams, in special Corina, and thank all you for your kind attention.
Thank you very much, Najme, for your interesting presentation. We have a few questions from the audience that I will run by you. The first one is, you mentioned the limit of detection and limit of quantification in the analytical performances. Are they for PFAS, or can you say something about that? Are they specifically for the PFAS?
You know, the limit of detection that we reported, it was just for measuring of PFAS, that we found 90 nanogram per liter. So I don't know if I answered the question, or...
Sounds clear to me. And the next question is, what is the change in current response for PFAS in the table with the interferences?
Okay, you know, for example, when we check the interference, as I told you, first, for example, we did record the current in absence of any interference. So after adding again, I mean, in the solution, we had, for example, 2 nanomolar of PFAS and, for example, 2 nanomolar of P4, for example. Then we record again the current, not just for one time. Of course, we repeat this for 3-4 times. And then we compare the change of current with and without this, I mean, examine interference.
Okay, yes. There's quite a few questions, so we'll go through them quickly, I hope. The next one is, can the sensor also be used in wastewater or surface water?
Actually, for example, when we did this, we started with the, I mean, tap water, and because, I mean, the matrix, of course, it was more clean than surface water. But yes, now we are doing to develop the sensor for using in the real sample in wastewater, in the, I mean, in groundwater, and the other also sample.
Okay, excellent. And is the sensor already on the market, or is it still in a development phase?
Actually, not in the market. I mean, the pink office in university, they have the license. But for doing marketing, if somebody it is interested, then maybe I can, I mean, introduce them for, I mean, doing next works for having, I mean, this marketing.
Okay, thank you. There's quite a few questions coming in, but we also have a very interesting second presentation. If you have posted a question in the chat box, don't worry, you will receive an answer to those questions via email by Najme. We will make sure they are forwarded and answered. Thanks a lot again, Najme, for your presentation. At this moment, I would like to move on to the next presenter and the next speaker. is Dr. Tali Harif, Chief Commercial Officer at Purefinity. And throughout her career, Tali has been involved in the development and marketing of innovative technologies for clean tech markets across the globe, either through large corporations and consulting firms or by directly supporting startups such as Purefinity. Tali, by all means, the floor is yours, and I will get your presentation up.
Okay.
You're good to go.
Okay. Well, first of all, thank you very much for inviting me to present today, and thank you everybody for joining this webinar. I appreciate there may be some overlaps between some of the PFAS wider issues that Najmi has already touched on. I'll try to keep those brief and focus on the treatment elements. I'm also aware that we are slightly short on time at the moment, so I'll do my best to make this quite quick. So the focus of this presentation will be to really touch on PFAS in water and the challenges that it poses, but also the opportunities. Just for everybody's knowledge, Purefinity is a London-based startup that develops advanced materials, and our focus for the past 2 or 3 years has been PFAS. So, in terms of PFAS, we know it's a very large group of chemicals, 4,700. They've been around for decades. That means they've been released into the environment for decades and have accumulated in the environment for decades. They were designed to be very, very robust and resistant, and hence they're non-biodegradable. And the carbon-fluorine bond makes them extremely persistent, hence the nickname Forever Chemicals. We're looking at industrial processes, manufacturing processes. There are more than 200 use categories just in manufacturing for these substances. And obviously from a regulatory and a treatment perspective, this makes things very, very hard to address, because small variations in the compounds can make treatment just very, very different. The previous presenter touched on this. So again, we're looking at subsets and groups. From a regulatory perspective, the non-polymer PFAS group is the group of interest, and within that, the perfluoroalkyl substances is the group of interest, because they are considered the most persistent, and they're considered the group that causes the most health impacts. Again, this is around addressing the regulatory requirements, and obviously regulations have been derived first and foremost from the health impacts, looking particularly at the sulfonic acid and carboxylic acid end groups. There are other functional end groups in the PFAS groups, but again, we're focused on the carboxylic acid and sulfonic acid end groups. Now, in terms of PFAS structure, again, small variations will cause changes in the properties of these materials, which from a treatment perspective will make things very, very challenging. So just in general, as you probably all know, we're looking at a very, very, a carbon chain that's been fluorinated, fully fluorinated. We're looking at perfluoroalkyl substances with a functional group at the end. So we've got one hydrophobic section of the molecule and a hydrophilic section of the molecule. Once the hydrophobic chain is longer, it becomes easier to treat because the whole molecule is considered less hydrophilic. And again, looking at PFAS in general, we categorize long chain and short chain. Long chain, by definition, very generic though. You're looking at chain of 8 carbons and above is long chain, and chain of 7 carbons and below is considered short chain. PFOA and PFOS, which are the most widely regulated compounds, are C8, and regulations are now moving towards the shorter chain PFAS, which are far more difficult to remove. So the regulatory environment is moving very, very fast, but there are gaps at the moment in the treatment technologies that are able to treat the short chain PFAS. Now, in terms of where Europe is in the PFAS crisis, I'd say Europe is probably slightly behind the US. The US has been dealing with this since the early 2000s with the famous Parkersburg incident, when it became apparent that DuPont had actually disposed of PFAS waste into a nearby river, and the population in Parkersburg had a very, very high cancer rate. There were two films. I don't know if you've seen those films, but I can recommend that you do watch them. It provides a very good, robust history of how this problem has emerged. And I'll just, Karina, are you able to play the trailer?
You knew. Still, you did nothing.
Almost heaven, West Virginia, Blue Ridge Mountains.
Hi, Grammars.
What are you doing here?
Your grandma tells me her grandson's some fancy environment lawyer down in Cincinnati.
I am a corporate defense attorney.
So?
I defend chemical companies.
Well, now you can defend me.
How many did you lose?
190.
190 cows.
You tell me nothing's wrong here.
It's a small matter for a family friend. Help a guy who needs it.
The farmer or you? That's chemicals, I'm telling you.
I'm seeing documents I don't understand.
They're hiding something.
That chemical, what if you drank it? Drank it? It's like saying, what if I swallowed a tire?
What if whatever's killing those cows is in the drinking water?
That's DuPont. Better living through chemistry. It's our DNA.
You need to tell me what in the hell's going on.
DuPont is knowingly poisoning 70,000 local residents for the last 40 years. You knew, still you did nothing.
You want to flush your career down the toilet for some cowhand?
You want to take everything that you know and turn it against an iconic American company, like an informant. Isn't that right? Isn't that right? Isn't that right?
Yes. They have all the money, all the firepower, and they'll use it. I know. I was one of them. Our government is captive to DuPont. They're trying to force you to make me stop.
He was willing to risk his job, his family, for a stranger who needed his help.
The system is rigged. They want us to think it'll protect us. We protect us. We do.
Okay, it's quite dramatic, but it is worthwhile watching. We move on to the next. So again, this is not a problem that's just confined to the US. It is a massive problem around the world. I don't know how familiar you are with general statistics, but this gives just a kind of overview of where things are, in a very brief way. That there are obviously other places with other issues. The US has an interesting site. If anybody's interested, the Environmental Working Group does have an interactive map showing all the contaminated sites that have been identified in the US. Again, the military bases in the US are an emerging concern, with already over 600 identified as being contaminated with PFAS. In the EU, at least 100,000 sites have been identified as PFAS polluted. And just looking at exposure, we're looking at hundreds of millions of people only in the US. So think about it on a global scale. This is massive. The UN has found in a representative study, and can assume now that 99% of humans do have PFAS in their blood. In terms of exposure routes, major exposure routes are A, drinking water, and B, food chain. So in terms of dealing with the drinking water issues, that is obviously an immediate an immediate concern. And I'm happy, the EU is now moving towards regulating, and by changing the Water Framework Directive, we're seeing a positive move towards getting this addressed properly. So, very briefly, I'm not going to touch on all the health effects. This is in the public domain, and but say the C8 science panel that was formed following the Parksburg incident, which was reflected in the trailer that you just saw, did find definitely six disease categories associated with PFAS exposure. Interesting enough, since then, lots of work has been done, and since COVID-19, lots of work has been done on the effect of PFAS on suppression of the immune system, and there has been a connection found between higher risk COVID cases and PFAS exposure. In terms of the cost to the EU, Nordic Council of Ministers published a few years back a very, very good, robust report stating horrendous sum of 84 billion euros per annum goes on treating health effects from PFAS exposure. So this is quite startling, to be fair. If you look at the PFAS cycle, very briefly, this illustrates quite well, I think, the various ways PFAS can enter the environment. Obviously, industrial manufacturing, disposal of illegal disposal of waste into water courses, or even legal disposal of effluent that will flow into a wastewater treatment plant, but the wastewater treatment plant does not have the technology that's available to treat PFAS, and it would just move through the wastewater treatment plant back into the water courses and accumulate over time. Obviously, one of the most one of the biggest issues is found around airports with fire training zones, use of AFFF, fire foams, and lack of containment of fire zones. So that's runoff water that's entered the environment and gone to infiltrate groundwater. Also, the use of sludge that contains PFAS in agricultural applications has caused infiltration into groundwater, and landfill leachate is an emerging problem that needs to be dealt with quite quickly. Next slide, please. So in terms of regulations and challenges, and from a treatment perspective, obviously the regulations will dictate what needs to be done. We're seeing a move up till now, up till about 1 or 2 years ago. PFOA, PFOS were highlighted as the compounds of concern. So C8, relatively long chain PFAS, and now everybody's moving into towards regulations to regulate shorter chain PFAS. As I mentioned, the EU Water Framework Directive has now amended how to address PFAS with 0.1 ppb for 20 PFAS compounds. This needs to be implemented within 2 years, and it needs to be transposed into international legislation within 2 years. And in the US, there's been a lot of pressure on the EPA that hasn't really done a lot to create a maximum contaminant level. So the advisory limits have been, only advisory limits have been 70 ppt for PFOA, PFOS combined. And actual states, so these 12 states have taken the step to create MCLs for their states to be able to ensure that their populations have safe drinking water. There are also restrictions, other restrictions coming out, and some PFAS compounds are already restricted from manufacturing under REACH. So there is quite a large, there's a lot of activity in the regulatory arena, and obviously from a treatment point of view, it's very hard to keep up with some of these regulations. So a very flexible platform really needs to be formed to be able to address these fast-moving regulations. Now I'll move slightly into the treatment arena and what we see as current solutions and some of their issues. So generally, and I'm not touching on everything at the moment because we don't have too much time, we're looking at adsorption technologies, which would be GAC, granule activated carbon, ion exchange, membranes, which will be typically nanofiltration, reverse osmosis, or low pressure reverse osmosis, and advanced oxidation processes. All of these technologies were never designed specifically for PFAS removal. And you need to keep that in mind, because PFAS is such a difficult compounds to remove. The fact that they're trying to adapt technologies that haven't been designed for PFAS kind of means that you're not able to have reliability in your treatment design and application. And we see that across the board. So when looking at treatment, we keep in mind three major parameters, which would be selectivity, affinity, and capacity. And selectivity is key to be able to remove PFAS and to be less prone to interference from other constituents in the water. Affinity is key, well, specifically in absorption processes, where you want a very good binding kinetics between your target compound and your adsorbent material. That will dictate your contact time, which will dictate the footprint, and the capacity will be how much can that media actually absorb. That will dictate your frequency of change outs and operational costs. Next slide, please. So if you look at GAC in general, GAC has been used quite a lot for long chain PFAS removal, and in some cases it can do a good job. It's reliant on hydrophobic interactions, but that means if you have high levels of organic matter in the water, it will perform not as well. Also, because of the low affinity between PFAS, specifically longer chain PFAS, and GAC, you're looking at double contact times that are needed to design a robust GAC application, which means your costs, your capital costs, and your operational costs are gonna just go up immensely. So for PFAS applications, carbon is used. However, the footprint is very, very large. It cannot remove effectively short chain PFAS. So when looking at regulations at the moment and how they're moving towards the shorter chains, we know that there's going to be issues with carbon. It can last, in best case scenarios, up to 50,000 bed volumes. Obviously, the spent GAC needs to be regenerated. You lose about 15% of that and need to supplement that with virgin GAC. And as I said, it can be very, very susceptible. So the use of GAC, although it has been promoted, needs to be really taken with a pinch of salt. I'm going to show a little graph from a recent publication showing the differences in GAC performance dependent on the PFAS compounds. And in general, we can see it follows a trend. The longer the chain, the better the removal. There will be some differences, and that depends also on the type of carbon and on the water matrix you're dealing with. Next slide, please. So ion exchange is also being used for PFAS removal. Again, not designed for PFAS, has been adapted for PFAS, reliant on electrostatic interactions. Contact times will typically be between 2 to 3 minutes. Obviously, that means it's a smaller footprint compared to GAC, and it can, in general, remove PFAS better than GAC. It's more expensive. The unit cost is more expensive, and the spent resin needs to be incinerated. One of the major disadvantages is that it's very highly susceptible to interference from other water constituents. So any complex water matrix with any negatively charged compounds will impact negatively its performance. Next slide, please. So the obvious technology would be reverse osmosis. It's extremely expensive, and it really wouldn't be economical for large volumes of water. It can remove effectively 99% of compounds, PFAS compounds. It's a size exclusion mechanism. Taking into account, we're looking possibly at 80% removal recovery ratios. That means 20% of your entire volume goes towards a brine reject stream, and that needs to be dealt with. So that's quite a challenge, because that means it's quite a high volume of water or brine, concentrated brine, that needs treating. Also, in addition, membranes from an operational standpoint, it's quite complex operations and are quite susceptible to scaling, fouling, depending on your specific water matrix. That means you really need to pre-treat well, and obviously that inflates the cost of your treatment train. If we go to destruction, destruction, and this is focused on advanced oxidation processes. Focus here is on water treatment. There are technologies such as supercritical water oxidation that can treat very, very concentrated streams, lower volumes, but they wouldn't be applicable to just treating a bulk of water, say a water utility needs to treat. In general, extremely high capex and opex, energy costs are very, very high. It's not a selective process, and you also have to be sure you're generating complete minimalization, because otherwise what you'll get is toxic byproducts or end products that even could be harmful. Big issues are around also the heating up of the systems because of the high energy and the rapid scaling and fouling that can hinder performance. So again, this isn't something that would be recommended to apply for PFAS, really. It has been considered, and there are papers on it, but not from a practical perspective, not very well recommended. So where do Pure Affinity come into all of this? So our approach is to design materials from the bottom up with focus on the actual compounds, the target molecules we want to remove. And that means to be able to do that, we need to address, again, selectivity, affinity, and capacity all at once. So it's not about adapting, we're not adapting a technology, we're creating a modular design and high selective binding of PFAS target molecules. The chemistry that we do is transferable, so we can change our substrates, and sometimes, depending on the application, we may, and we talk about large volumes of water. We also do work in the point of use market, which is smaller volumes of water, and we'll be using different substrates for that. In terms of the targeted interactions, we're looking to utilize the full scope of types of interactions. That means hydrophilic, electrostatic, and hydrophobic. That would mean that you're creating a material that has high affinity towards your compound of interest. And obviously the capacity will depend a lot on the substrate we select, and the porosity and the ability to functionalize inside the pores and create a large surface area. So that is our approach. We'll be starting pilots, one in the US, one in Denmark, towards the end of July, August. And again, it's not a one-size-fits-all solution. We're not developing one material for all PFAS. We acknowledge there'll be a difference between, for example, long chain, short chain, and we'll have to apply different approaches to each, but also combine technologies. So looking at carbon could be a great way of roughly pre-treating the water before applying a polishing step. And so these are things we do consider when looking at a full application and how to tackle it the best way, looking at a full treatment train, and obviously the costs associated with that. So the value proposition at the end, Karina, can we go down to the last slide? Thank you. Would be to generate an application that can tackle broad spectrum PFAS regulations. That means both long chain and short chain, that can tackle interference from water constituents, that has high capacity. That means the media can be utilized for an extended period of time, and that the operational complexity is rather low. And also from a life cycle cost perspective, it would make sense. It has to make sense. So I think that's all for now. Thank you very much for your attention.
Thank you very much, Tally, for your presentation. Also for you, we've received a few questions.
Okay.
The first one is, can nanofiltration also remove PFAS?
It depends what type of nano. So a tight nano, well, there are overlaps between reverse osmosis and nanofiltration. So you would say a tight nanofiltration membranes essentially can be a low pressure reverse osmosis membrane. So I would say yes, but it has to be tight enough to remove PFAS. But it's still not cost effective.
I see.
So if you look at it from simply a performance point of view, just performance, it can remove, yes.
Okay. Next one, are the novel materials applicable to drinking water preparation, especially when considering microbial regrowth?
Well, there's a question around biofouling.
Yes.
The biofouling will occur in any filter. So filters are not made from carbon, so carbon is very high. They're not made from materials that are a carbon source for microorganisms. It doesn't mean microbial growth won't occur, but the idea is not to keep water in the filter stagnant. You have a flow-through application, and you do apply the regular methodology that's needed when dealing with any filter to make sure it's maintained and kept operational.
Yes. And then the last one is the technology with the materials also suitable for wastewater treatment?
No, we wouldn't recommend putting an adsorbent in a highly organic concentrated wastewater effluent. We are working on a project with a wastewater treatment plant. However, the effluent is being robustly treated beforehand, and our technology is being implemented as a polishing step. So you would need to remove most of the background organics to be able to have then an adsorbent that would work well. But that's to my point, that we need to combine technologies, look at the application, combine technologies, and see what would be the best way to address the full application end to end. And our technology isn't the silver bullet for everything. It's definitely targeted towards PFAS, but it has to be designed in combination with other technologies that are going to help the application succeed.
Yes, clear. And then one more last one. When will the novel materials be available for testing?
We will be starting testing in August.
Okay. And if anybody's interested, they can contact you.
Absolutely.
And you'll be happy to discuss things further. We'll make sure that we exchange those email addresses so you can discuss matters further. Okay, and with that, thank you very much, Tally, again for your presentation. With that, we come to the end of our webinar for the day. I would like once again to thank our speakers, Nashme Karimian and Tally Harif, for their contributions in their presentations. And of course, thank you to our audience very much for listening and asking the questions. The recording of this webinar will be made available on the Sensilo platform, and you will all receive a message when the recording is available online. We also invite you to check the Sensilo's event page to see what events will be coming up next. The good news is that after the summer, from September onwards, we're planning to restart our physical meetings, workshops and trainings again, so they will take place in addition to the digital meetings that we have been having for the last 18 months. So we hope to welcome you all again soon at one of our next events. And for now, thanks again to everybody and enjoy the rest of your day. Goodbye.
Okay, thank you.
Thank you.